Today I will discuss some preliminary definitions related to symmetry operations. The first item is principal axis of symmetry. The highest fold axis of symmetry of an object or molecule is called the principal axis of symmetry. For example, if you consider BF3 molecule, like this, here there is the boron atom and these are positions of fluorine atom. Now this molecule has one three-fold rotation axis which is perpendicular to the plane of the molecule. This is the molecular plane and the C3 axis is perpendicular to the plane of the molecule. There are also C2 axis. These BF bonds act as C2 axis. Therefore, the highest fold axis is C3 axis. This is the principal axis for BF3. In case of water molecule, there is only one axis of symmetry, which is a two-fold axis. Since there is no other rotation axis, this C2 axis will be considered as the principal axis for water molecule. For benzene, the C6 axis perpendicular to the plane of the ring is the highest fold axis because the other symmetry axes are two-fold axes like this. There are six other C2 axes, but there is only one C6 axis which is the highest fold axis. This is the principal axis for benzene molecule. There may be molecules where we cannot find any principal axis. For example, in the methane molecule, this is CH4. Each and every CH bond acts as a C3 axis. Therefore, we cannot determine which one is the highest fold axis. So, in this case, there is no principal axis. No principal axis. Our next item is horizontal and vertical planes of symmetry, sigma H and sigma V. Horizontal planes are those planes of symmetry which are perpendicular to the principal axis. And vertical planes are those which contain the principal axis. In case of BF3, the molecular plane is a plane of symmetry. This plane is a plane of symmetry and it is perpendicular to the threefold axis. Here there is a threefold axis perpendicular to the plane of the molecule and the molecular plane sigma is perpendicular to that. Therefore, this is denoted by a subscript H. This is a horizontal plane of symmetry. And there are three other planes of symmetry like this. If we extend this plane, it will contain the highest fold axis, C3 axis, and it will cut the molecule into two equal halves. So this is a plane of symmetry, but it contains the principal axis of symmetry. So it is a sigma V plane. Similarly, there is another sigma V plane containing this BF bond and the principal axis. There is another sigma V plane containing this BF bond and the principal axis. There are three sigma V planes and one sigma H plane for BF3 molecule. In case of water molecule, there is only one C2 axis. This is the principal axis of the molecule, and the molecular plane is a plane of symmetry. This plane contains the C2 axis, therefore this molecular plane is a sigma V plane. Similarly, there is another plane of symmetry for this molecule. This plane also contains the C2 axis. Therefore, this is also a vertical plane. Both the planes, in case of H2 molecule, are sigma V planes. In case of methane, there are planes of symmetry. For example, using these two bonds, you can imagine a plane like this. Using these two bonds, you can imagine a plane like this. It will contain these two bonds, and if you extend the plane, it will cut the molecule into two equal halves. One bond will be on this side and the other bond will be on that side. So this is a plane of symmetry. But since there is no plane of symmetry, therefore this is neither sigma H nor sigma D. No subscript is needed here. It is simply a sigma plane of symmetry. Our next item is order or period of a symmetry operator. Order or period of a symmetry operator. If a symmetry operator R is such that when executed n times successively, it produces the identity operator, then n is called the order or period of R, symmetry operator R. For example, the C3 operator. C3 operator, when carried out 3 times, will produce identity, a 360-degree rotation. So order is 3 in this case. For any Cn operator has order n because Cn n times implies a 2 pi rotation. A reflection operator carried out 2 times produces E. Therefore, order is equal to 2. An inversion operator carried out 2 times produces identity. Inversion carried out 2 times will produce identity. So, order is also 2 in this case. Now, the interesting case is an improper rotation. Consider S3. S3 is actually equal to sigma perpendicular C3. If your molecule is a BF3 molecule, then this sigma perpendicular can be written as sigma H. I am taking this as an example. Sigma H. Then what is S3 square? S3 square means sigma H C3 again sigma H C3. We know that these two operators commute. Therefore, we apply commutation rule once. Keep this unchanged and apply commutation rule here. then we have sigma h C3 square sigma h. Then again apply commutation rule here. Sigma h C3 square. And what is that? These two will give E C3 square. So this is C3 square. Thus S3 square is not an improper rotation actually. It is equivalent to C3 square, a proper rotation. Then S3 three times. S3 three times will produce sigma H C3 three times. This means by applying commutation rule here and simplifying, we get sigma h C3 square sigma h, and here we have sigma h C3. Now these two will give identity. So sigma h C3 square, then identity C3. This is equal to sigma h. This is identity, and these two when combined will produce identity C3 square. C3 means C3 three times is identity. So our result is sigma h. S3 three times is sigma h. S3 four times means S3 three times into S3. S3 three times is sigma h. We have just obtained. This is sigma h into S3. Sigma h is sigma h, and then S3 is sigma h C3. This is identity, therefore this is C3. S3 five times is S3 four times multiplied by S3. S3 four times is C3. You have got it here, and then S3 is sigma h C3. So this is sigma h C3 square. This is a genuine composite operation. So S35 is really an improper rotation, and it is equivalent to sigma h C3 square. And then S3 to the power 6. S3 to the power 6 is S3 to the power 5 times S3. This is equal to sigma h C3 square multiplied by sigma h C3. And then again applying commutation rule, we will get sigma h square C3 three times. This is identity, because this is identity and this is also identity. So we get identity only after applying S3 six times consecutively. Therefore order of S3 or period of S3 is 6. If you increase the power here, you will get these operations back, because S3 to the power 7 is S3 to the power 6 S3. This means S3, because this is identity. if you go on increasing this exponent, this power, then you will get these symmetry operators back. So the operators are repeated again and again after an interval of 6 times execution. So the 6 is also called period of the operator S3. We have a general rule. Sn operator has order equal to n for even n and equal to 2n for odd n. We have verified this just now, and to verify this, let us consider S4 operator. This is sigma perpendicular C4. S4 square is sigma perpendicular C4 2 times sigma perpendicular C4. By rearranging using the commutation rule, we have sigma perpendicular square C4 square. So this is actually C4 square or C2. We can stop only when we get E. So we have to continue. S4 to the power 3 is S4 square into S4. This is C4 square. You have got it here, C4 square into sigma H C4. This is sigma H C4 to the power 3, a genuine composite operation. And S4 to the power 4 is S4 to the power 3 times S3. This is sigma H C4 3 times. Again sigma H C4. This is equal to, these two will produce identity, and these two again will produce identity, C4 3 multiplied by C4. So finally we get identity. Therefore 4 is the order of S4 operator. So this is verified. When n is even, n is the order of Sn. Our next item for discussion is the inverse of a symmetry operator. Inverse of a symmetry operator. If R1 and R2, if R1 and R2 are two operators such that R1, R2 is identity. The two operators carried out successively produce identity. Then R1 is called the inverse operator of R2. R1 is the inverse of R2. So alternatively, R2 is the inverse of R1. Whenever two operators multiplied produce identity, one is the inverse of the other. For example, C3 square multiplied by C3. Multiplied means executed successively. If the result is identity, then inverse of C3 operator is C3 square operator, and inverse of the C3 square operator is C3. Sigma, a reflection operator, is its own inverse. This is its own inverse because two reflection operators on the same plane will give identity operator. Similarly, the inverse of inversion operator is also inversion because inversion operator carried out two times about the same center of symmetry will produce identity. And what is the inverse of S3? What is the inverse of S3? We know that S3 multiplied by S3 to the power 5 is identity. We have obtained this result just now. Therefore, S3 inverse is S3 to the power 5. And the reverse is also true. Inverse of the S3 5 operator is S3. So with this much of preliminary definitions, we can proceed to symmetry, multiplication, etc. We will consider those in some next video. Let me stop here now, and I thank you for watching.